this one. Sorry. We'll keep on doing the quickly now these load cases. And what you see on the board now will be the production notes. We'll finish the previous one first. Let's see. I just had a sneak peek in the drill ahead is basically just to see uncover what the new mud weight is going to do. Normally what you're afraid of is that if you change your mud weight drastically, you will have different pressure regimes over your casing that you just set. You typically talk about deterioration of the mud. After approximately a month, in casing design, we say that the mud is completely deteriorated. So in the top it will be water, in the bottom it's completely sagged out. And that's something to think about when it comes to integrity, because the weight particles in a poor quality mud is like sand, and this sand will make your casing completely stuck. It's just as good as any cement when it comes to integrity. Experience-wise, you cannot rely on that as an integrity base, but in reality, that's what it is. When formation collapse, typically shales and typically sagged weight material, your casing is as stuck as if it was cemented. And that's why P&A is very hard when you're cutting the casing and you're trying to retrieve it. It's stuck, and you have to cut small sections. Yeah. Drill ahead. You're just checking the conditions. How does my casing look? I drilled it with say 1.3, and my next section, so 1.3 would be what this was cemented with. So there's a little bit of cement, and then 1.3 in the annulus, and on the inside, the next section, whatever it is that you're drilling with there, it could be 1.1 or it could be 1.9, anything in between, right? So that's what you're just checking, and normally that's not a very hard or a demanding situation for the casing as per se, but you have to do it. Cementing in itself, you check what is going on with the pressures while this very heavy fluid goes into place. Also, rarely any difficulties when it comes to cement design. On the other hand, when you're doing your drilling design, this is the hardest hydraulic test of your open hole through the cycle of the well section. Yeah, the highest hydraulic force on the formation during cementing. Lost returns with mud drop. You guys know what that means, I guess. Say that you have total losses, and what we do in that case is per industry standard, or what has been adopted over to governing documentation for many companies, will be to set the mud level with the specific weight you have. Let's say that it's 1.5. Then what you do is to again, a casing, open hole. Here is your pore pressure equivalent to 1.5, and that's gonna take your mud level down here, right? So your mud is now in balance with the pore pressure of 1.5 at the bottom. Now you have cement here, and you have some sort of drilling fluid outside here, and then what you investigate basically is the force going in this direction. It could be a burst load, it could be a collapse load. All right, lost with her with running hole. That one is a little bit important for you as drilling engineers, but you don't really do that in the casing design applications. There are two things you need to know and take away from running hole. One would be, well, let me ask you guys, what do we need to concern ourselves with running hole? And it's not really part of the casing design software, but yeah, surge pressures, very good, thank you. Surge and swell, right? And remember the difference between a floating rig that goes up and down all the time and a fixed something. Yeah. Also, another factor that is important.
The steel going down.
Yeah, yeah, returns so that you have the kill control thing. Yeah. More. Sorry, well control. So you have the, that's better to say. So you have control, well control at all times. Yeah. Yes. We could go a lot more deeper into that point there. It's very important. I can just do that because you guys are. This is your casing going into your well. Like this, say that you have previous casing here. When do you refill it? When do you fill it up? Yeah. You fill every stamp, but do you fill it up? What would be the limit? Yeah. When do you have to fill it? Yeah. No. Yeah. But it's not going to collapse, even if you run it to bottom. It's true what you're saying, so that will be one, but what I'm after was what he said. Yeah? Yeah. Normally we have a check valve here, like this, so that we can fill, right? And if the level, if this one fails, suddenly mud will flow back. And if the volume inside here is so little that the mud level will go below balancing the pore pressure, you will have a kick. Yeah. But that's not part of the casing design. I just got triggered by your comment of well control. Yeah. Sorry. Useful anyways. I guess that has not been taught. Was that a new point for you guys? Yeah. I thought so. That's why I said it. Running hole. Horsepower on the rig, and your string up. How much can you pull? How much can you pull? You guys have probably calculated string weights, right? And when it comes to drill pipe, it's nothing. Casing is the heavy part, right? Yeah. If your casing is stuck, how much can you pull? What is the regulation for overpull, right? You understand what you see what I'm getting at? If you do your design and you say that my rig can pull 300 tons, no problem, 350, right? And what is the string weight? It's 250, right? How much can you pull? You can pull 100. Is that enough? Is that going to be enough? There's no jar in this, and you can't start jarring on a casing string either, right? So this is what you think about when you do the running hole. But you're not doing it in this software, it's in the torque and drag module, right? Yeah. Overpull, that's the set overpull that I reflected on just now, right? And casing as per se today, in old times when, and that's what has been, what you'll find in many of the softwares, it's the BTC connection. The threads called BTC. They are very, very simple, and I would say they are used by some still today, but they are in many contexts what we call an obsolete thread. Very, very basic, and not, they are limiting pressures and actual forces what the casings can take. Whereas modern premium connections, they are stronger than the casing itself. So that's why me, for many cases, I often tend to forget to the connection part of it because I know they are stronger, right? So, but that's dangerous. Don't do that. All right, overpull. You need to know the actual stress that you're going to have on the casing as per se, and the casing is able to take that, right? The purely actual pull. And rig for that matter. Post-cementic static load, again, also the pre-cementic cementing static load, both of them in the same category as drill ahead and cementing. They are not really demanding load cases. They could be in very, very special cases, so we have to do them. But so far, I have never seen them setting any precedent to what we should pressure test to. Lenient testing. Casing evacuation. Behind that one is basically gas injection. Gas injection. If you for some reason get a leak in your gas injection system, all the gas will disappear and there's going to be nothing in your well, right? I'm now talking about gas lift wells, right? Because the gas lift will go to a certain depth, and then there is a check valve there. So from that check valve and up, you will have nothing in the annulus. And in the tubing, you may have a fluid, and in the annulus of the gas lift casing, there will also be a fluid. And you need to understand what this means. Casing evacuation. Because the lost returns with mud drop, that covers the drilling situation. And then we can think, okay, what's going to happen in production, right? Full evacuation, you can also think about it as, well, there's one that is actually missing, and that's casing evacuation. That one should be a production load, and what is missing from the drilling loads would be injection down casing, meaning that you are injecting cuttings. Have you guys heard about that part? There are something called a smack unit. Smack unit. Don't ask for abbreviation, but basically what it does, it takes the drill cuttings for oil-based mud. It grinds it up and slurrifies it, so it becomes like a cement slurry, slightly viscous, and then you pump it down your casing into, for example, a formation like Utsira. Then you don't have to take the cuttings onshore for processing, which is a very expensive procedure. Tubing leak. That is very often the load case that is the most extreme for all wells. Normally, there are exemptions. For example, a field called Kvitebjørn, it has its highest pressure. It's an HPHT field, but the reservoir is depleted and not very high pressure, but the 12.25-inch section above has extreme pressures. So that one is that one is kind of an exemption situation. But tubing leak, our casing, our tubing in the production packer, we have a leak in the top. We have our brine, completion brine. it could be 103 SGs. On this side, we have 1.4 SGs, maybe. And on the inside, we have either gas or oil or whatever it would be. Here, the rest say that the shut-in pressure, shut-in bellet pressure, 150 bar, which is very low. Piston, it used to be 990. So I'm here. Let's say that there's a density of 0.6 SG on 150. That means that you have 103 down here. You have 103 plus this pressure on top. So you have it starts the pressure curve for this casing will be 150 bar here, and then the curve for 103 going down like this. Okay, and of course it stops at the packer, which then puts it down to 0 like this, 0, and then under it will be typically there's an opening here for a liner, right? So it would be the reservoir pressure and the liner height. Where do I? Yeah, I'm not gonna be fast going. So now we have. So then you can start to make that drawing. Pressure-wise, it will be the same as the reservoir, corrected for the fluid depth here and so on. And that's how what we are going to go to. We're going to just have a look at these typical curves, how you make them to see. This is what you will again get in the casing design software. Yeah, these curves. Clean up, first flowing of the well. What's typical there is that there are brines and residual muds and whatever that will be in the tubing and down in the well. So it's a different pressure regime. You can do that, and also it's the initial reservoir pressures. Early life production phase. You have a very high rate. You have what you do and what is important at this point in time is this geothermal gradient. Let's say that the geothermal gradient is like this, and when you start producing, the temperature that you get in the well, it starts here, and it goes almost to the same level as the reservoir. Say that this is 150 degrees Celsius. Then typically, if it's a high rate well, it will be 100 to 145 degrees Celsius on top, right? Which is going to give high thermal stress in this case. You're going from typically here 4 degrees on your wellhead if you're subsea. That's at the bottom of the sea always, and you're going up to 100, 145. It gives you quite a lot of thermal stresses, right? And that's part of producing, starting the cleanup. Yeah, a lot of thermal stresses, and not to forget, in this annulus here, the A annulus and the B for that matter, all of them, we say that for 1 degree heating, there is 1 bar increase. As like a field rule of thumb. So we always have to control our annuli, bleed them off as we heat the annulus. Yeah. In this case, for us, it helps a little bit with old wells to have a small cushion of gas on top, because the gas compresses and the pressure doesn't go as fast up, right? Yeah. Midlife production, late life production, you guys get the idea. Midlife, reduced reservoir pressures, and late life, very low reservoir pressure, depending on the pressure support from injectors and so on. You just need to think through all of these things, ask the questions, get the input, and make sure you have done your job. Yeah, following these load cases. Shut in short and shut in long. The difference would be, any idea?
Shut in the weather will cool down.
Exactly, it's the temperature. Yeah, it's the temperature. So you get a difference in temperature going on there, and you need to do some considerations for that. Active annulus, that's the gas injection. Bullheading, that's killing. Yep.
You consider wellhead fatigue with this, like if you shut well in and you release and you shut it in.
No. So we don't do well fatigue as part of that in the casing design. We don't do that. Well fatigue, to my understanding, and that's what I have to answer you. It's a very good question. I have never considered it. That's my answer to you. Some may do actually, but I don't think so. Why? Because there was an incident in an old well where they had poorly cement on the production casing over to the conductor, so that there were some leeway there, and they put up these old enormous BOPs without any support. The wellhead had to take all the stress, and you have the ocean current going like this, and you have the frequency swaying of the riser. It broke off the whole wellhead. Yeah, that happened many years ago, and that's when they started talking about wellhead fatigue as a huge problem. Yeah. Since then, there are so many mitigating methods. Don't know if you have been looking into or talked about them, but what you do is that you tie down your BOP and you offload the wellhead. That's how you reduce the fatigue issue. Many ways of doing it. I've seen a couple of designs to mitigate the wellhead fatigue. But the production-wise, no, I don't see that this actually do the wellhead fatigue. What that comes down to is how the nature of the wells are, because it goes in the bottom of the wellhead also. We can have a quick just look at as a drawing. Remember last session when we looked at how these things interlock. The PGB, permanent guide base, looks like this with the conductor sitting in it like this, and then the wellhead comes in like this with a 20-inch surface casing in it inside, and they look together here. In principle, what we saw on land-based wells, the starter head in the previous slide is basically the same. It sits like this, and it sits only on a few beams on the, I promised to find the name, but I forgot. There would be the, is the name of that first pipe again? It's installed with the well pad. just a construction piece, normally a few meters only. And then comes the conductor here, cemented. And then comes that's the starter head with it. And then comes the main wellhead part here with the surface casing. And they also lock in here at the bottom. The forces that comes, they go up along the casing, of course, and goes through this locking point and down into the conductor that is cemented into the ground, and the forces pushing the well up is held down through this what is called a lock ring, and the lock ring rating is part of, call it, advanced casing design. I know that this class is called advanced casing design, but then I have to say that the advanced casing design. Then we are modeling the lift and the shear forces in the wellhead, for example. Yeah, and that's another software that we are not going to use in this class. We used to do that in the autumn in that other class. Then we were running WellCat, which is the advanced portion. Yeah. All right. Bullheading, that's just pumping down, pushing back whatever's in the tubing towards the formations. Kill operation, then you for sure have typically fluids that are heavier than the pore pressure. And then the stimulations, mini fracs, breakdown to X slots, and also proper fracturing. Yeah. All right, those were the different load cases explained. You can now just start to think about and look forward to modeling this yourselves. You'll get curves like this. This is before tubing leak. Let's have a quick look. So here we see the production packer, pressure, reservoir pressure. We typically see the tubing. It's a little bit poorly written. You guys can't see this. Yeah, it's the packer fluid inside and in the annulus, and it's the differential pressure it's trying to say here. And in the tailpipe, it will be zero. The differential pressure before and after tubing leak would look something like this. I'm not gonna. We're not gonna dwell too much on this. I think. Excuse me. You see the leak in the top here and how the formation pressure goes in. This yellow one here is the production. Sorry, production forces from the reservoir. What you're producing. Yeah. Yeah, that would be the shut-in pressure. Yeah. Yeah. And this is what it looks like. It would be zero differential pressure at the leak, right? Before and after. So a collapse pressure as the packer fluid now is on the back of the tubing, and it goes down to with the same gradient as the packer fluid. This blue line should actually have been taken away. That was the initial fluid before producing, right? Should have taken this away because this is the actual line on the inside. Yeah, that's a problem, putting too many things at the same time. Acting forces on casing. Any questions? I mean, you can study these curves and so on, and that's going to be part of the lab that we're doing, hopefully. Acting forces on casing, internal pressure could be either applied or by nature, external surface pressure, typically applied pressure testing, so on and so forth, whatever you're doing of things. External density profile, any buckling, and there's a big difference between helical and sinusoidal buckling, of course. Internal density profile, casing wear and corrosion. The top of the cement plays an important role. It very often is drawn, as we saw with the production packer here. Uh, yeah. Yeah.
I had a question if it's possible to rotate the casing down to reduce
Action.
the friction.
Yeah. We do that with liners, normally not with casing, because casing is so extremely heavy and large that rotation is very it's limited to the makeup torque. The makeup torque that you put in your threads would be the limit of how much torque you can put in. And casing very often is so high torque that you will immediately reach the makeup torque, and it basically hasn't started rotating. Whereas with a liner, it's a different story. Yeah. Yeah. What has been locked into the cement while cementing, you get some differential densities, and you can lock that actual stress into the tubulars. Running in buoyancy differences, external pressure profile in cement, kind of yeah. All of this is what we will look into in the lab a little bit, and as much as you guys, when you have had an introduction to the software, you can look at it yourself also. Actual tension and compression, gravity of pipe is normally the greatest source of any actual stresses. You also have thermal expansion for the innermost casings and tubing. Then that's the the highest contributor. External internal pressure regime and changes, reverse ballooning effect, so on. Yeah, that drawing is going to come where we're seeing a pressure test of the annulus, how it squeezes the pipe and it becomes thin. Uh, the OD reduces and it elongates. That's the natural state of the reverse ballooning, and the opposite for ballooning. Yeah, in belt paths you'll have bending. We'll have a look at that too. It creates a local stress regime. High friction, ledges, mud quality, effective hole size are things that contributes to higher friction. Buoyancy, fixtures force. Buoyancy is actually a very advanced topic that has been discussed for so many years. In effect, um, the preferred and the easiest way is just the Archimedes way. You put 1 liter of steel into the well and reduce it with 1 liter of the fluid that you have. But how the forces turns into stress in the pipe is a different story. Shocks. If you say that you have a glass plug in your well and you release it with pressure, have you heard about glass plugs and these type of things? It's a plug that you pressure up to a certain pressure, and then you bleed off that pressure, and then you do these cycles for a number of times, and then there's like a detonation that happens to it, and it explodes, and it turns into very fine sand. These things are very useful when you are doing completions, for example, and they're often used more or less something like this for every single well. And what happens when you have a high pressure in a well? is that there will be like a water hammer. This water hammer, Joukowski equation is called, gives you a shock through your pipe. Yeah. Pressures, change in density, degrading of mud in the annulus, change of fluids from drilling completions to other fluids, change of production fluids composition. Let's say that you have water or gas breakthrough of your produced fluid. Temperature increase in the annulus from production or injection, change in formation exposed to the well. Let's say that you do perforation into a new formation. Excuse me. Surface applied pressures, collapsing formations in situ stress, and the water hammer that we just talked about. These are pressure forces that act on our casings. Very quickly look at the buoyancy equation. This is very standard, very simple, and you guys know this very well. I'm not gonna go more into it. Axial stress, you also know this one very well. I'm not gonna go into that either too much. Bending stress, that one is a little bit more unfamiliar, I guess. Just stop me if I'm saying something wrong, if my presumptions are off. If you bend the stress, you'll see a curve like this. Sorry, bend a piece of pipe. You'll see a curve like this. Typically, the blue line that we see there, for one thing, this is the depth. This is the typical torque and drag curve that we see. Surface weight is up where the blue interact the horizontal curve, and going down, the tension reduces. It becomes zero at this point where it crosses the vertical line marked as depth, and it's compression where it goes over to the left. Now, what we have is a small dogleg in this stapled line here, marked in red, and with the curvature that we see in the blue frame, what is on the inside of the pipe, we have a compressional force. On the outside, we have an additional tension. In our case, we want to know what is the extreme. Going down to zero, we add the tension. Going from top down to the neutral point of the pipe, we add. Whereas when we go into compression, we would typically add the compressional part, right? That's only natural because it's adding to the philosophy for casing design. We design for worst case, right? Yeah. Compression will only reduce the tension here, and tension will only reduce the compression of the pipe down there. So that's why we do it like this. Okay. An equation, I'm not going to explain those to you guys. You are very capable of doing that yourselves. Here is the ballooning. Again, very simple. Excuse me. An internal pressure will take you from that fully drawn line where the pipe is at its natural state, and it will go out to the stapled line. And at the same time, it will retract. The same thing is in the opposite way with the reverse ballooning. It will contract and extend. And the equation is very simple. The force of ballooning that you add is the Poisson ratio, internal pressure and area, cross-sectional area, and then the external force and the cross-sectional area, and the length and the gravity. Everything else is self-explaining here. You guys would simply understand that. Now, any load case that we set up is a combination of all the forces that you're talking about now. Now we are dissecting the load case, any of them. and we say that yes, there is bending on our pipe, and that is how we adapt pipe. There's at one point some ballooning when you're pressure testing. That's included in the load case, and thermal changes. That's included. Everything is included. Imagine if you're going to hand calculate these things as they did in older times, right? But you hand calculate all these simple contributions into your one load case, and you need to do these calculations for every single step. So kudos to the old guys, those who are retired now and still alive, to put it like that. All right. Yeah. Again, the thermal gradient, geothermal gradient would be in black, the full line, whereas the producing temperature in this well is the red staple line, as I tried to draw on the board earlier. And you'll see a lot of thermal stress. Typically, the highest contributor to stress in wells. And I'm gonna say it straight away. We are not going to calculate and model temperature changes in wells, because that's quite advanced. Then you need to have the specific heat capacities and everything else for every single component, and you need to know the phase diagram. When do you have free gas and not, and yeah, the composition of the hydrocarbons, as per se, it's a mess. But what you guys need to know is that there are three basic mechanisms. You have convection, radiation, and conduction. Yeah, that's what we have in wells, and they are making the change from that geothermal to that other curve that we saw, the producing red one. And basically what we can do and what has been given in the exam is this equation, and I tell you what the temperature change is, and you will calculate the thermal stress. Very simple. Equations for the different mechanisms are here. Again, you're not going to mess around with this. It's a very special case. What I can say is that the most advanced modeling softwares, they were made here in Trondheim. There are two of them. Schlumberger bought one, and the Sintef IFE guys, they are sitting with the other one. And they were made of, I don't know if you guys know this, but there is the multi-phase facility up in Tiller. That's where they were doing all these tests to make these multi-phase calculations. Yeah, so that's kind of interesting. I think we just stop here. We are a minute or two over the time. We'll just continue this this part. Where we are at now is that we are discussing and dissecting the load cases, right? Looking into them, what they are. All right. Any one of you who did not send me an email and want to have few of the presentations and eventually the live recordings, you drop me an email and I will respond to you. All right. See you guys on Tuesday. Yep. How it result? Mudless. Mud losses. I'm not sure that there will be any mud loss as per se. What this does it introduces stress into the casing. That is basically what it does. Say that we are for this case here pressure testing the weld. When you're pressure testing, we increase the pressure on the inside. What does it do? It balloons the casing, it makes it go wider, and it contracts in the bottom, right? And that's going to do something to our annulus. You understand? So if you pressure test something to 100 bar, expect something to happen in the annulus at the same time, right? You just need to know. And when you're pressure testing, expect also some stress to be going on in your casing. Why? Because you're pushing it out. And there's a relief part of it in the retracting. Now, if you have set the packer or if you have cemented this one, it is not free to move in the bottom, right? So it will transform into a stress. I should have said that. It's on the live recording. And you guys, yeah. So that's why, thank you for the question so much. Because I should actually have said that, right? Because if it's cemented in the bottom or set a packer or something, then anchored up in some way, then it means that, and in the weld head or Christmas tree tubing hanger, pipes are always more or less fixed in both ends. So any pressure or temperature change will result in thermal stresses inside the pipe. Does that answer the question? Good. Then I'm happy. I can actually draw straight on it. I didn't know.